So, hi everyone. Yeah, hey. So, thanks for being here. It's my first ever talk in the Hackfest. So yeah, today I'm going to talk about understanding digital certificate cybercrime exploitation. And I'm going to introduce our new tool, which is a decentralized PKI naming system on the Ethereum blockchain. So a little bit intro about myself. I'm a PhD student and a blockchain engineer at Concordia Institute for Information System Security. I'm from Montreal, and I'm also a research intern at the AMF, Quebec's financial regulator. I'm now working on decentralized order books, and I've given talk at FC, BTS Security Revolution, and Concordia FinTech Society, and I'm doing research on blockchain and fintech, TLS and CA trust model, and I'm doing also usable security stuff. So the talk today is about a paper that we just published at last year's FC conference. And here's the outline. I'm going to go through a PKI introduction very briefly. We talk about the existing issues in the PKI, and I'm going to show you the empirical study that I did on the CA ecosystem. And because of the issues that we found there, we moved into the blockchain. I'll tell you why. And I give you an introduction to the blockchain and then Ethereum blockchain more specific. And the new solution is called Azal. It's a decentralized application. And at the end, I do the performance and security evaluation, and then we have the future works. So what is HTTPS? We had a few talks, and that they talked about like TCP and SSL. It's like the protocol that we all use in our daily lives, in our daily communication, to secure the connection to the web servers that we are visiting over the web, like in our daily life. So this protocol provides message integrity, confidentiality, and the server authentication. The server authentication itself relies on a client's ability to obtain the public key, which is bound to the server that we are visiting. And in order to provide that, the current WebCI model relies on like some businesses or companies called certificate authorities or the CAs, and they're basically doing 3 steps on a paper. They receive certificate requests from domain names from everybody, doesn't matter who, and the most important step is to verify the ownership of these domain names. They have to make sure the person who's asking for a certificate for that specific domain name is the real owner of that domain, is the authoritative party. And at the end, once the verification is done, they issue the certificate for that domain name, and by issuing certificate, we basically mean they bind a public key to that domain name. Of course, there's a lot more in a certificate, but this is the most important thing. So CAs have issues. The first one is they have been targeted, like focused on targeted attack during the last few years. For example, Komodo and DigiNotar, they were hacked in 2011, and attackers were able to issue fake certificates for top-level domains, such as Google and Yahoo. So in that case, all of the communications from the client to those web servers were just intercepted by the attackers, which is very bad. The other one is the number of CAs has exploded. This is because root CAs can delegate the power of issuing certificate to the intermediate ones without anyone knowing. So we don't really know how many of CAs now exist on the web. It's really like it's hard to say except for scanning the entire web. And we know very little about them because there has not been a lot of research done, and all of these CAs are working like black box. Yeah, they're saying, yeah, we have 3 steps. You register, you fill out the form, and then we verify. But the reality is that they're not always doing the thing that they're saying. And the last one is, as I've mentioned, the intermediate CAs are invisible. There's no way of knowing how many of them are there, what are their names, what are their certificate practice statement, except for scanning the entire web. So what did we do was enumerate all these trusted companies. Why do I call them companies? Because they're basically companies. They're like issuing certificates to the public directly, and we formulate a detailed documentation of the existing validation mechanics, and we started designing and implementing a decentralized PKI and naming system for the web on the Ethereum blockchain. So the first step is to identify all the existing CAs. I got a short list. I got a list actually from Microsoft Windows, Apple, and Mozilla, all the root CAs. And after merging all this data and collapsing different identities for the same CAs, I got a short list of 259 unique root CAs. And I did the same for intermediate CAs, except for, because as I've mentioned, they're invisible. So I used the other major research project, EFF, CMAP, and Certificate Transparency from Google, and I got a short list of 446 unique intermediate CAs. So we have around 700 root and intermediate CAs. We want to identify the companies, those ones that issue certificate, because there are a lot of them that they don't issue. And so to do that, I went to each and every one of them manually. I researched, and I found that only 223 companies issue certificate to the public. The rest, either they issue the certificates internally or they're managed by different CAs. And I've mentioned that these domain control validation, they are like black box. So no one really knows how is it. So what I did was I created my own website using the domain. This was a workshop registration website. So a user would go there, create an account, pay for the workshop. So it would make sense for the CA that I really need a certificate for my domain. And I started buying a regular 1-year single domain certificate from each and every companies that we got. So the result shows that only 71 of these companies actually issue certificate to the public. And out of these 71, 42 of them are willing to issue domain validated certificates, which is a great issue. I tell you why. And I found that companies do not always document their CPS, which is like, it was obvious, but no one has really like looked into it. So we proved that. So as I've mentioned, 41 of them out of 71, they are willing to issue DV certificates. So the web still runs largely on domain validated certificates. And it's bad. Why? Because in terms of these kind of certs, CAs are not authoritative over who owns what domain more than you and I. And I found that there's no actual single party that is authoritative. There's ICANN, they're managing top-level domains. Then they delegate the power of registering domain names to the registrar. And registrar, when they want to give domain to users, they don't verify the identity. They have username and passwords, and we know passwords. And then there's CAs, they can be registrar or some other parties, and they're also dealing with passwords. So not security is kind of the issue here. So we found that certificate authorities rely on indirection to perform domain ownership verification. So how? Let's look at the domain validation itself. So in the old days, if a person would want to prove that he owns the domain.ca, they would either call the CA, or they would go to the CA. So it was in person. It was great from the usability perspective, but from the economic perspective, of course, it's not easy and it takes a lot of steps. Nowadays, email-based is the most popular way of doing domain control validation, in which the CA would send some secret, a validation token, to some email addresses they assume it's controlled by the domain owner. And if the domain owner can access this email, the verification is done. Let's dig into it. So in order to send a validation email, CA needs to have the IP address for the mail servers of the domain name of that email. And they consult with the DNS and they get the IP address. Who puts the IP address here? It's put by some registrar, and there's a person out there who has a password to this registrar who's affiliated with domain.ca. So once the CA gets the IP address, they would send the email and it will go to a mail server first. There's again another person here who's the password to this mail server. Maybe it's the same person, maybe it's the different one who's also affiliated with domain.ca. And at the end, the email would end up in somebody's mailbox. We hope it's the domain owner. And if the domain owner can get this email address, the validation token, which is secret, means that the verification is done. So if we carefully look at this picture, we find that there are 2 levels of indirection. And each level is vulnerable to some security attacks. For example, there are passwords here. There's some users, they can log in. So if the attacker can break the password, they can break the validation. The other one is CA needs to have a good view of the DNS. And if the attacker can poison the DNS or do other attacks on the DNS, then he's done. Great. The other one is we have secrets, so confidentiality matters. But SMTP protocol uses opportunistic encryption, which is not really secure against active adversaries.
And at the end, I told you, CAs have some lists of email addresses that is affiliated with different domain names, but it's really hard to hold in reserve this kind of email addresses. And sometimes the domain owners do not even know that these email addresses exist and they're being used by some people out there. So yeah, these are the list of threats to email-based validation. So there has been solution for this. Some people were doing detective or protective schemes, but we started thinking about this issue a little bit different, like on the blockchain. So I'll tell you why. First, a little introduction to the blockchain. Blockchain is a peer-to-peer network, and it's run by a lot of computer. Anywhere in the world, they can join anytime they want. They can leave anytime they want. And transactions are being validated through the consensus of the network. And once the transaction is validated, they're there forever. Nobody can change it. So it's an append-only sequential data structure. It's distributed consensus mechanism. And new blocks can only be added at the end of the chain. You can't go back in the chain, in the middle of the chain, and change a block. Why? Because that needs a lot of computational power that not everyone has that. But Ethereum blockchain is the word computer. Why? Because it allows you to use the blockchain. Instead of using it as an append-only broadcast channel, now you can run code on it in a decentralized manner. It has the Ethereum virtual machine that allows you to write and run programmable smart contracts to the Ethereum blockchain. And smart contracts are written in a high-level programming language called Solidity. So how did we use Ethereum blockchain? Just imagine a scheme in which the domain name itself would be issued through the blockchain. Who would be authoritative over this domain name? Of course, it's the blockchain itself. So we created and designed a new uni-authoritative paradigm that resolves indirection and authority issues. It's a smart contract-based naming and PKI system. And it enables users to fully manage and maintain control of their domain name and also their certificates without having to rely on any trusted third parties such as registrar or CAs. And it's decentralized, so names cannot be reassigned without the cooperation of the owner. So our decentralized application is called Azal. And in this system, users can register their domain names. We have registration fees, which are against domain name squatting. They can also renew their domain names, and for that, they have to, again, pay the registration fees. And they can transfer their domain names as well. And they can do it through either auction or transfer domain names. Auction process is where I leverage the programmability of the Ethereum blockchain because I used inheritance to create a child contract of our main contract. And here's how we implemented the auction. As you can see, each auction can be at any stage of open, locked, and ended. That's because we didn't want the domain owner to run auction, let's say, on an expired domain names or on a domain names that is already being under auction. So user can run any number of auction on any number of domain name they have, but once auction at a time on each domain name. And yeah, so they can do it through the auction or they can do it through the transfer domain name. And that's basically through calling the transfer domain function. And when you call this function, it basically changes the Ethereum address that controls the domain name. And owners are free to decide to either transfer domain names associated attributes such as TLS certificates or not. They can provide it either with a previous value or with 0. Yeah, here is how I implemented the transfer function. As you can see, there's something like called modifiers here. That's modifiers are the ones in Ethereum block in Solidity that allow you that every time you want to run a function, you can create a modifier and it applies certain conditions. So if the conditions are met, then it allows you to run and execute a function. So why did I use that? Because in the Ethereum blockchain or any blockchain, there's no notion of time. Because it's decentralized, it's a peer-to-peer network, so there's no notion of time. So you can say this domain, specific domain name is going to be expired in 2 years. There's nothing like that. So there's only way that you in 2 years you come here, you call a function at this domain name, and it marks this domain name as an expired. There is a service like Ethereum Alarm Clock to do that, but I really didn't want to rely on any trusted third parties in system. So what I did was I created a check domain expiry modifier. I put it at the beginning of every function in the smart contract. So every time a domain owner would want to do anything on that domain name, this modifier will go through, and if the domain name is expired, it can just mark it expired, and it either allow or doesn't allow the domain owner to run the function. So we have this modifier. We have another one that doesn't allow the domain owner to transfer the domain name if it's unregistered or expired, and the other one is only the domain owner can transfer the domain name here. But you can see that modifier only owner. So the other things the domain owner can do, they can assign arbitrary data to their domain names, and because it's decentralized, these values are globally readable, non-equivocative, and not vulnerable to any indirection attacks. And these values include TLS certificates, and we use multiple size arrays. So a user can assign multiple certificate to her domain name. This is for load balancing stuff. And they can also add DNS files to add resource records to domain name. But because storing a lot of data on the Ethereum blockchain is not economically efficient, they would add it on a server somewhere, and they provide a hash of that file on the blockchain for further file verification. And here's the primary states and transition for domain name. So you can see the domain name have these different states. That's because we want different functions to be executed when domain names are at different specific states. So at the end, I implemented a cost evaluation to see how much to compare, how much does it cost to register a domain name and to get a certificate in the real world versus in this new system, which is built on the Ethereum. So the smart contract is implemented in 370 lines of Solidity language, and I tested it on the Ethereum test network. So you can see here, to register a domain name in our system, it only costs $3.15. Whereas in the real world, for GoDaddy, for example, it would cost $20 per year. And to get a certificate, for example, it would only cost $1.43, whereas in the real world, you have to pay around $80 per year. And because smart contracts are very much vulnerable to security attacks, we also did a security analysis on our code to make sure that it's not vulnerable to any known vulnerabilities. And we used a security analysis tool called Oyente. And we tested it against different bugs, parity, call stack, depth attack, and also transaction ordering and stuff. And these falses here show that it's not vulnerable to any of those attacks. This is actually a great security tool. I really recommend it to anybody who's coding on Ethereum blockchain. And as I've mentioned, there have been solutions to this CA, and some of them are blockchain-based. And for example, there's Namecoin, but Namecoin only offer name services. You can only register domain names in a decentralized manner. There are Blockstack and Certcoin. They're built on the Namecoin, so they add some PKI extension. You can register your domain name, you can get certificates, but there are on Namecoin, and Namecoin is Bitcoin altcoin, so you can't run any code on it. So there's another one, Ethereum name service, that it provides a name service, and it's built on the Ethereum, so you have programmability, but again, you don't have PKI functionality. So here we are, we offer name service, we offer PKI functionality, and we are built on the Ethereum blockchain, so we have programmability. You can add another functions to this system. So the future works could be for those ones that are interested in this research, they can work on the scalability and understanding the issues of the scalability and how to minimize the amount of data a client needs to fetch from the Ethereum blockchain every time they want to look up a domain name. And actually, we're currently a research group looking at the domain name front running, because in blockchain, especially in Ethereum, miners can censor transactions, so they can easily do the domain name front running. So we're looking at that now. And another one is user interface. You can create a user interface, it should be very easy. And the other one is because it's built on the Ethereum blockchain and you have programmability, there are a lot more functions to be explored. And thank you. If you have any question for me. And I forgot to mention, our code is open source on my GitHub, so you can use it anytime you want. Sure.
So how does the renewal work? Because you said that there's no time-based. It's not time-based, right?
Yeah.
So when it expires, if you don't want to do any maintenance on the domain and you don't want to call any functions,
Yeah.
how does it expire?
One of our design decisions is like that when the domain name expires, it still continues to function, but you can't do anything on it. You can go like auction it. You can do add any certificate. So a domain owner would really want to, if he wants to do anything, he should pay the registration fees again. Yeah. Okay. Thank you.